Today is December 7th, 2021, and a lot of what you're about to see was recorded last December, December of 2020. If you are in the Monday morning class, this is just really review for you, all right? I've put it on your blackboard, but we've already gone through this in class. If you're in the Monday night class, 5:30, then we didn't have class yesterday because of the Monday night football game at the stadium. So day class ran, night class got canceled. We can't really afford to get that far behind. So what I'm doing is, this is the video that goes for my hybrid class. I'm making it available to you. I'm putting it on your blackboard so that you're not a week behind with, really no time left in the semester. So this is really my way of not missing that week for you guys because of the football game. And obviously, if you're in the hybrid class, then this is the way you're normally getting the classes. So nothing strange. The only thing you'll notice about halfway through, it switches from one video to another. I've kind of combined two. I think actually I grow a beard instantaneously somewhere along in there. I think I start out clean shaven and then poof, next thing you know, I'm grubby. Anyhow, the information is good. I've deleted things that have to do with just last year when everything was remote. I talked about the labs. I've probably gotten rid of all of that. I'm not sure. So this video is going to run almost 2 hours. No reason you can't, pause it, take a break somewhere in the middle of it. This is much longer than my normal video, I know. But what I'm trying to do is I'm trying to get everything covered before the semester ends. And realistically, we have next Monday. That's really about all we've got. Today's the 7th. Yes, so yesterday was the 6th. Then it's the 13th. That's the next time the classes actually meet. The next Monday we have. And then the 20th is really close to the end of the semester. So by the 20th, I want to have the final out there. I want you taking the final by then. So it's all done before the semester ends. I think the semester ends on the 23rd, something like that. So again, if you're in the hybrid class, the AU-264-HS1, this is just normal for you. If you're in the AU-264-0C, this is just review. We already talked about it. Well, we talked about half of this in class yesterday. And if you're in AU-264-5B, because of the football game, you missed. So hopefully this gets you caught up with the day people. There's no real time, to do that in person. So as always, and this applies for all of you, whether you're on the online class or the seated class, if you have questions, email me. I'll do my best to answer them. If I can't answer them by email, we can do a one-on-one WebEx or Zoom or whatever, and you can ask your questions and I can try to answer them. So whatever it takes, I just want to get through the end of the semester with trying to cover everything, but I don't want to rush it. I want you to understand it. And I want it so that I can give you plenty of time to take the final. I don't want to give you the final on the 20th and you'd have to have it done by the end of the semester. You'd only have a couple days. I want to make sure there's enough time. So important that we get this material covered. What doesn't get covered, I'll remove from the final. But if it's on these videos, it's fair game for the final. So here's the latest lesson. It's one thing to be able to fix a car, to be able to bolt on new parts or whatever, but what really makes you valuable as a tech is your ability to do diagnosis. decide what is it that we need to fix. And even though there's all kinds of onboard diagnosis now, that doesn't mean the cars just tell you what parts are needed, right? They kind of point you in a direction, and then you've got to finish the job yourself after you get a code. So diagnosis is, half art, half skill. What you're trying to do in as few steps possible is take some sort of perceived concern that the vehicle owner or the driver has, understand what the concern is, and then figure out what's causing it and what the corrective action is. So if we go through here, right? So this presentation is entitled Drivability Diagnosis. So I guess we want to talk about what is drivability. I see I have it spelled incorrectly. Sorry about that. So what is drivability? It refers to the smooth running of the engine. If the engine does not run correctly during all phases of operation, it's said to have a drivability problem. So obviously, if you have flat tires or things like that, it does affect the way the vehicle drives, but we don't call those drivability problems. We would call those, suspension problems, steering problems, brake problems. Drivability is really about how the engine runs. And so there's a set list of symptoms that we call drivability symptoms, and I'll list those in a bit. It should be noted here that some symptoms can also be caused by problems with the transmission. I'll give you a little story. Back in the early 80s, I guess, I worked at a dealer where we sold the Renault Alliance. That was a 1984 Motor Trend Car of the Year. Kind of calls into question how they determine Car of the Year, but anyhow, it had a unique, for that year, for 1984, electronically shifted transmission. That was very uncommon in 1984. And this electronically shifted transmission had a problem where it had a fuse that supplied the transmission computer. And if that fuse, for whatever reason, popped, the transmission would default to high gear. Now imagine a 1.6 liter engine trying to start a vehicle out in high gear. If you've ever been on a bicycle and forgot to downshift before you stop, and you try to get going again, very, very difficult. So these Renault Alliances, if they try to start out in high gear with a little 1.6 liter engine, very, very, very sluggish, very hard to get the car moving, right? So the symptom, right, that the customer is going to complain of is a lack of power. The vehicle just won't accelerate. So it is a drivability symptom. Lack of power is definitely a drivability symptom, but the cause is it's not an engine performance problem, right? It's a drivability symptom, but it's not an engine performance problem. It's a transmission problem. So we see things like this sometimes. You could actually get a drivability symptom like lack of power. Think about it this way: if you've got a dragging brake, so a caliper is seized, that might give you a lack of power concern from the. You got to keep in mind a customer doesn't know what's causing the problem; they just know what it feels like to them. So if the vehicle won't accelerate or has trouble getting going or keeping going, they're going to call that a lack of power problem, and it may be caused by something other than an actual lack of power. So I just wanted to point that out before we moved on. So here are a bunch of drivability symptoms. So no start. A no start comes in two flavors, two varieties. So I want to make sure we identify one is really an electrical problem and the other is a drivability problem. So if the starter cranks the engine, we call that crank, excuse me, crank but no start. If it's a no crank situation, where the starter's not functioning, the starter motor's not functioning, that's not really a drivability symptom. That's an electrical problem. So when you see no start listed here, we're talking about starter cranks the engine over, but it doesn't begin to run. Hard to start. So usually that's extended crank time. It doesn't want to start, but eventually it does. Stalling, typically we think of stalling as an idle problem. You come to a stop sign, you come to a red light, puts off the gas, engine quits running. Frequently, it's accompanied by the next symptom, rough idle. So if it's idling poorly, it's more likely to stall. I have seen engines, though, that just stop running driving down the road, so maybe it's running at 2,000 RPM and all of a sudden it loses, ignition for some reason, or it loses fuel. Maybe the fuel pump dies, right? So I don't really call that stalling. That just quits running, right? Stalling, we're really thinking more when you come to a stop, you're at idle, it idles poorly and then quits running, right? Hesitation on acceleration. You step on the accelerator, you don't have an instant application of power. There's some sort of a delay. Misfire can typically be felt as roughness in the engine. It can be worse on acceleration. You may not even feel that misfire when the engine is idling in park or neutral. If it's mild, if it's severe, you will. So misfire, what it means is that one or more cylinders are either not firing at all, we call that a dead misfire, or they're not firing well, so the air-fuel mixture is not lighting completely. Lack of power, I already talked about that a bit, right? It's just the engine does not accelerate, the vehicle doesn't accelerate at the rate you would expect it to accelerate at. Surge is kind of a weird one to describe if you've never felt it, but this is a situation where the power from the engine is inconsistent. So it begins to accelerate, and then the power falls off, and then it picks back up again, it falls off. So you have this feeling that, it's almost kind of push-pull feeling in the driver's seat. Idle speed problems, obviously, idle speed could be too low, could be too high. If it's too low, you're probably going to have rough idle and stalling. If it's too high, you may have harsh engagement when it's taken out of park and put into gear. Warning indicators like the malfunction indicator light, that's a drivability symptom. Fuel economy concerns, very, very difficult to verify that. People may have unrealistic expectations, or another problem with fuel economy concerns is fuel economy numbers that are given by the EPA don't necessarily reflect real world driving, the way normal people actually drive their vehicles. So if you have somebody that's a lead foot, they're not going to get the kind of fuel economy that's listed on the EPA's website. And that's interesting. I don't know if you've ever gone to the EPA's website, but fueleconomy.gov, maybe I'll go there in a bit. And then spark knock, we talked about when we talked about compression and when we talked about ignition timing. And we know this is kind of another term for detonation. And we saw the video on detonation and what that kind of looks like and sounds like. So let me say this really, really clearly. We went over the four-stroke cycle. What is an engine doing when it's running? And what is it doing well when it's running well, right? Four-stroke cycle. Just think of this. If the engine's not running or not running well, it's not doing one of those four things well. Either it's failing to take in a good mixture of air and fuel in the correct amounts, or it's not compressing it properly, Or problem with the power stroke would typically, you would think ignition, right? Not lighting it correctly. Or a problem with the exhaust stroke. Plugged exhaust. In the lab, you didn't all get to see it. But some of you, we did the exhaust back pressure test on a Ford Escape. We pulled the oxygen sensor out, put a back pressure gauge in its place, ran the engine at idle, ran it at 2,500 RPM, and then using rags stuffed into the tailpipes, tried to increase the exhaust back pressure and see what it does on the gauge. So if the engine can't get rid of its exhaust, it can't take in more air. So that's going to definitely limit how fast the engine can run. So what can go wrong on the intake stroke? Well, if the engine is not getting the correct amount of fuel and air, right, we have throttle valve dirty or stuck. What kind of drivability symptoms could that give you? Rough idle, idle that's too high, right? A throttle actuator malfunction, possibly, you could have. What else happens on the intake stroke that can go wrong? Intake valve's not opening properly. What kind of things could cause that to happen, right? Maybe we have a worn cam lobe. Maybe we have a collapsed lifter. Maybe we have rocker arms on vehicles that use them that are bent, push rods that are bent. Maybe the valve timing is off, right? That's going to affect possibly only an intake cam, right? If we have dual overhead cams. So a lot of different reasons why the intake valves might not be working right. Mass airflow sensor not reading correctly. That's an intake stroke problem. That's really going to screw up the computer's calculations on fuel delivery. What can go wrong with a mass airflow sensor? Well, the sensor itself can go bad, obviously. Sensor can be unplugged, wiring problems to it. Another thing that can happen is what we call unmetered air, or other people have called false air, right? Which is air that's entering the engine, but the computer doesn't know about it. And this can happen if the plumbing between the mass airflow sensor and the engine has leaks in it, right? So air gets in through those leaks without going through the mass airflow sensor. The computer is not going to know about that air, so it's not going to add enough fuel. So there you go, plumbing problems, right? We could have intake manifold leakage. We could have, on more complicated, we have variable intake runners. Maybe they're not switching correctly. Holes in things, a lot of different possibilities, right? Vacuum leaks. We could also, part of the intake stroke on most engines is also fuel delivery into the cylinder, right? It is sprayed into the intake airstream, highly atomized. The time that this is different is if it's direct injected. If we move on to the compression stroke, what can go wrong on the compression stroke? Well, air-fuel mixture not being properly compressed, right? So maybe the valves aren't sealing. I think you all saw what happened on that Subaru motor interference engine when the timing belt snapped, right? All the exhaust valves are bent, so they don't close. So when the pistons come up on the compression stroke, it just pushes all the air right out the exhaust. So building up no pressure at all. If that timing belt had not snapped, if it had just jumped, or timing chains sometimes jump when they stretch, you could have improper valve timing. That can cause compression pressures to be really low. In the case of that Subaru, right, really low means we had zero. We had wide open valves on the compression stroke. if we have worn cam lobes, let's say we have a worn intake cam lobe, and we don't take in enough air, that can cause our compression pressures to be low. How about worn rings, bad head gasket? And I've seen worse. You know, we talked about pre-ignition earlier on, and in the one slide, you could see that if the pre-ignition went on long enough, it actually could burn a hole right through the top of the piston. And I've seen engines like that. I've seen pistons with holes right in the middle. And guess what you get for compression? Absolutely zero. So on the power stroke, right? What can go wrong on the power stroke? So our cylinder is full of a properly compressed air and fuel mixture. We have the right amount of air, the right amount of fuel. It's compressed to the correct pressure, but it doesn't ignite or partially ignites. Why? Maybe we got a bad coil, bad spark plugs, bad wires. Maybe the ignition happens at the wrong time. Maybe it happens late, maybe it happens early, right? So think about why the ignition could happen late. On older vehicles, it could be actually adjusted wrong. On a newer vehicle, you know, something wrong with the spark advance system. Maybe the NOx sensor is giving some sort of false indication, right? Or there's a NOx sensor code, so the ignition system won't advance the timing as much as it normally would, right? We could have the wrong fuel octane rating, right? So maybe we actually are knocking, and because of that, that's a bad problem on the power stroke. What else could go wrong? Think about it. And then lastly, and this stroke gets kind of, ignored a little bit, but the exhaust stroke, right? So after the air-fuel mixture is burned, if it's not effectively cleared from the cylinder to make room for the next air charge, we're not going to completely fill the cylinder, and we're not going to have a good combustion event in that cylinder. So what could cause the exhaust stroke? What could go wrong with it? Exhaust valve doesn't open or doesn't open fully. Maybe we have problems with the exhaust cam lobe. Maybe we have push rods or rocker arms that are bent. Maybe the exhaust system is restricted. What could restrict the exhaust system? I talked about this in lab when we did the back pressure test, for those of you that did it. We need to talk about the way a catalytic converter works. So, how does a catalytic converter work? Pretty well, right? But catalyst is something that causes a chemical reaction between two other chemicals, but doesn't actually get involved in the reaction. So in the case of a catalytic converter, when unburned fuel coming out of the cylinder, right, there's always a little bit of unburned fuel. We call it unburned hydrocarbons. Because combustion is not 100% efficient inside the cylinder. So a little bit of fuel makes it into the exhaust. The catalytic converter's job is to take that unburned fuel and combine it with oxygen. And that oxidation process is caused by the catalyst, but the catalyst isn't part of it, right? Just in the presence of those materials, that platinum, palladium, oxygen, and hydrocarbons combine with each other. Completes the combustion, basically. A byproduct of that, of course, is heat. So a catalytic converter in normal operation gets extremely hot. When, for some reason, there's an excess of unburned fuel in the exhaust and in the catalytic converter, the temperature of the catalytic converter can become excessive. So what could cause an excess of hydrocarbons in the exhaust? Typically something like an ignition misfire. So that the air and fuel is not combining in the cylinder. It comes out of the cylinder during the exhaust stroke, hits the catalytic converter, and the catalytic converter, in attempting to make these two things combine, and that byproduct is heat, but it becomes excessive. It becomes really excessive. I've seen catalytic converters glowing red hot under the car. So inside, if you've looked inside a catalytic converter, the substrate is kind of a honeycomb design, and when it overheats, it can actually melt and become blocked. So instead of the fine little passages through it, they seal up from melted material, and now the catalytic converter doesn't let exhaust pass through it. Another thing that can happen, the catalyst can break up inside, and those chunks land in the muffler and block up the muffler. So restricted exhaust, probably the most common cause would be, a meltdown of the catalytic converter. There are other things. The muffler itself can rust out, and a baffle in the muffler could wind up blocking the outlet or something. Anything's possible, I suppose. Somebody could, run over a curb and bend their exhaust, squeeze the pipe flat. I've seen things like that. Back into a snowbank, bend the tailpipe over, back into a fence or a snowbank or a pole or something like that. So anyhow, if the exhaust becomes plugged, the biggest symptom will be lack of power. So let me go back to the slides here a minute. And I gotta share that. Turn me off. Okay, so the question was, exhaust system is restricted by what? Well, the answer to that question is, of course, probably the catalyst. But it could be some sort of physical damage to the exhaust. So if we're going to figure out which, right, we've got all these possible problems, right? Problems on the intake stroke, the compression stroke, the power stroke, the exhaust stroke. Now it's up to us. We have a drivability symptom, right? There was this whole list of symptoms here. Customer comes in and presents us with one of these symptoms. And believe me, they're not necessarily going to use the correct terminology. They just might come in and say it runs bad, right? So it becomes your problem then to convert what they're saying to fit one of these actual symptoms, right? So they might say it runs bad. Well, you might find out that that's misfire, or you might find out that it's a rough idle. So what do we have to do? Well, first thing, verify the condition. How is this done? A lot of times, if you're working in a dealership or you're working in a larger shop, you may not have any direct contact with the customer. So you get a repair order, and the repair order says, car runs rough. And that's it. And a lot of this depends on how good your service writer is, right? So whoever wrote that repair order, if they're experienced, if they're good, they're going to ask questions. So the repair order is going to say, rough idle when it's cold, right? It's going to identify the conditions that it happens under. Maybe it only happens when it's cold. What do we mean it runs bad? Well, it's a rough idle. So they may give you better information, but a lot of times you just get something very, very basic. And so depending on the work environment you're in, maybe you can speak directly to the customer, try to clarify, when does it happen? What exactly are you talking about? I have in the past gone on road tests with customers so that they can kind of point something out. I'm going to suggest if you do that, you do the driving, because I was a victim of a irate customer who launched us off the ground one time. I won't go into details about that, but I decided anytime I went on a road test with a customer, I would do the driving from then on. So how else can we verify the condition, right? Well, we can drive it ourselves. We can ask questions of the customer. We're trying to identify exactly what the customer's concern is. Now, this is not a drivability thing, but sometimes the customers, we don't really know a lot about cars. So let me give you an example. I clearly remember having a vehicle a customer bring in a brand new Lincoln Town Car, complaining about a rattle. And I drove the vehicle, and in the trunk, I could hear the jack and spare tire just bouncing around back there. And I thought, oh, okay, this is an easy one, you know. So I brought it back. I opened the trunk. I went in there. I stowed the spare tire and hooked it down the way it's supposed to be with the jack, so it wasn't moving around or anything like that. Returned the repair order and keys back to the service writer. Wrote down what I did. Thought that was great. Customer took the car and was back shortly after saying that I hadn't done anything to fix his rattle. And, he wasn't even paying attention to that stuff bouncing around in the truck, which was very, very loud, very loud. Instead, he was complaining about this tiny little sound coming from under the dash. So it's really important that before you try to fix a car, you understand what it is you're trying to fix. I worked at a Lincoln Mercury dealer, and so, we had everything from, town cars, big cruiser, down to the Mercury Lynx, which was the Mercury version of the Ford Escort. And safe to say that if you've been driving a town car for years and you trade that in and buy a Mercury Lynx, the smoothness, performance, and everything else of your new car is probably not going to meet your standards. And so, I had this happen where customers thought that their new car had a rough idle problem, and really it's just a difference between a nice big smooth V8 and a little four-banger. There was nothing wrong with the car. So you could spend days trying to fix a problem that just really doesn't exist. So here's what we were told, and you should. Let me actually get my face back on here a minute. So if you're working somewhere, you need to find out what your shop's policy is on this. We were told in no uncertain terms that if we couldn't verify a concern, right, if customers said that the car ran rough and we drove it and it didn't run rough, we were absolutely not to try to fix the car. If it ain't broke, don't fix it sort of thing. So we were instructed to write on the repair order, no problem found, and return the vehicle to the customer. And the reasoning behind that is once you make an attempt to repair something, then you're kind of admitting that you agree with the driver that there's something wrong. And if there's not actually something wrong, there is no way you're going to be able to fix it, right? So you're putting yourself in this no-win situation. You might think, well, I didn't feel it misfiring, but let's throw a set of spark plugs in it. Or throw a set of wires on it, or replace the coils. It's warranty, what the heck, right? Well, once you do that, now you kind of own that problem. When the customer says, no, it still runs badly, and you can't now say, well, I didn't notice any problem with it. It's like, well, then why did you try to fix it? Why did you replace the coils? Why did you replace the whatever it is you did? So this goes right back to that statement, verify the concern or verify the symptom, right? So you have to know what it is you're trying to fix. If you don't know what you're trying to fix, how will you know when it's fixed, right? If you've made no change, you won't know when it's fixed. So verify the condition we just finished talking about. Attempt to operate or attempt to operate the vehicle in the same conditions the customer experiences the problem. Does the concern only happen on a cold engine, only under load, etc.? If you cannot duplicate the concern, you may ask the customer for more information or have your service writer do that. So next, and this has changed over the years. When I was working in the dealership, and that was a long time ago, diagnostic trouble codes were the very last thing that we ever looked at because the onboard diagnostics were bad. They were kind of primitive. So they can be fooled very easily by mechanical problems. Still run into this occasionally, on more modern cars. Give you an example. My daughter had a Jetta, and that Jetta, shortly after she bought it, used, but it had it had a warranty on it. So it popped up a check engine light, and it was still under warranty. So I could have just taken it to the dealer, but I wanted to see what the code was for. So I just put a scan tool on it and looked. And the code was for coolant temperature sensor. So obviously I didn't fix it, since it was under warranty, but I knew what they were going to find when they plugged it in at the dealership. And so it went to the dealership. They obviously found the coolant temperature sensor code, and they replaced the coolant temperature sensor. I might as well turn this back on. As long as I'm just talking to you, right? So they replaced coolant temperature sensor under warranty, cleared the code, gave the car back. Everything seemed fine for a couple of weeks. I don't remember the exact time frame. This is 10 years ago, 15 years ago. So they cleared it. She drove the car for a while, and the light popped back on. Sure enough, another code for coolant temperature sensor. So went into the dealership under warranty. They replaced the coolant temperature sensor. Is that crazy? Is that ridiculous? No, it's not, because new parts have been bad. It happens. But anytime something like that happens, you should be kind of suspicious of it, right? That's not super common, especially with all the quality control they have in place nowadays. So car comes back, another few days, weeks, don't remember exactly. The light comes back on. Sure enough, it's a coolant temperature sensor code. So they, this time, they decided they would put a new connector on the coolant temperature sensor. So the thinking, the logic, I guess, was it must be intermittent, right? It's not the sensor. It must be a problem with the wiring connector. So they put a new connector on it, cleared the code, gave it back. And then over a period of time, the light came back on. And that was when I decided, all right, I need to look at this. So put a scan tool on it and ran the engine, and I watched the coolant temperature sensor reading, and what I found out is it never ever hit operating temperature. So the real problem with the vehicle was the thermostat was stuck open a little bit, and so that the engine wasn't reaching its normal temperature, and the computer was flagging that as a sensor. Well, the code indicated that it was probably a sensor, but it really was never the sensor. The sensor was correct. What was wrong was the actual coolant temperature was wrong, right? So put a thermostat in the car, and that code never ever came back. Contrast that. So that was a 2003 Volkswagen. I've seen 2015, 2014, 2015 General Motors. So we've gone another dozen years improving on onboard diagnostics at that point. And same problem, bad thermostat, but it didn't give a coolant temperature sensor code. The code it gave was engines not reaching operating temperature. And so that kind of points you more towards the thermostat, right? So the point I'm trying to get across is onboard diagnostics back in the early 80s were horrific. Not horrific. They weren't very sophisticated. Onboard diagnostics now are much, much more sophisticated and much more likely to point you closer into the actual cause of the problem. So when I was being trained, when onboard diagnostics was new, we were told checking for codes was like the last thing you do. And I think that story I told you about the Jetta, the Volkswagen, it kind of explains why. Had we just made sure that the vehicle was actually getting hot, just your basic cooling system problem. It's same system that's been around since way before computers, we would have known that the computer or the computer system or the sensors was not the problem. So, so that's how I was taught. And then over the years now, I have become a believer that onboard diagnostics are a lot better. And so I do agree. So let me go back to the slide, right? Give it a minute here. I agree that retrieving diagnostic trouble codes after you first verify a symptom is now a valid order of doing things. Do this early. Because onboard diagnostics are so much better now, this is really, really likely to point you in the general direction of a problem. Or you're going to find there is no code whatsoever. And it's absolutely possible you have a drivability symptom without any kind of a code. So no code diagnosis is something you have to be able to do too. So what do? We use a scan tool, retrieve and record all diagnostic trouble codes. I haven't really told you what a hard fault and a soft fault is. I spend more time on this in the spring semester, but just quick and dirty explanation. A hard fault, the problem exists right now. And a soft fault, the problem may be intermittent. So it's set a code, but as you check the vehicle out, you may not find the problem to exist. So think of a loose wiring connection. You hit a bump, it flags a code, or it heats up and separates, and it gives a bad reading, flags a code. But when it's sitting in your shop and it's cool, the problem doesn't exist. Or here's a really common one, soft fault. Somebody leaves the gas cap loose. It sets a code, evap leak. Then the next time they fuel up, they tighten the gas cap. They bring it into the shop because the light was on. You see the code for the evap leak, you're never going to find it because it doesn't exist right now. That's a soft fault. On the other hand, a hard fault is, let's say that the filler neck is rotted out. You're going to find that. The problem's going to exist when it's sitting in your service bay. So one of the ways, there's, the different car manufacturers have different ways of separating hard fault from soft fault. Older Chrysler had something called a good trip counter. And if it showed 0 good trips, that means it fails every time it runs. So that's a hard fault. Now they call hard faults active and they call soft faults stored. General Motors uses the current for a code that is a problem that's happening like on this particular trip or drive cycle. Call it current as opposed to history, which is something that happened in the past. Ford always had what they called on-demand codes, codes that you could force a self-test the computer to run through its diagnostics, and if it come up with a code right then, that means the problem exists right then. Or it would give you continuous codes, which means part of the continuous self-test that happens while the car is being driven snagged this problem. Doesn't necessarily exist right there in your service bay. So if you have a hard fault, if you erase the codes and it comes right back, it's definitely a hard fault, right? So since you may be erasing codes as part of your diagnostics, it's a good idea to make sure you record all of them, write them down, or take screenshots or something. Get out your phone, take a shot of the scan tool screen so that you don't lose any information. You may want to refer back to that. If a lot of times one problem can create multiple codes. So another thing, before you do any kind of erasing, you might want to look at freeze frame data. That's something we'll get into in more detail. But when you erase the code, you're going to erase that freeze frame data too. So be careful about that. Don't get rid of information you're going to wish you had later. If you have a combination of hard faults and soft faults, obviously start with the hard faults first. Fixing those may take care of everything. And generally speaking, if you have several codes. Whichever one comes out first, jump on that one. Now this semester in the shop, we had a weird, it was a Honda Odyssey van, if I remember right, and you know, one of you owned it, and so you know, I don't remember, but there was a code for the motor mount. This thing has active motor mounts, you know, so the motor mount was bad, and it would not allow you to continue on with the diagnostics for the other code. And I don't remember what the other code was, but you couldn't follow that code chart until you fixed the motor mount and got that problem taken care of. So sometimes you're forced into an order. Okay, so now you've verified the condition, you know the problem you're trying to fix. You know whether it exists right now or whether it happens only sometimes. You know what conditions maybe it happens under. This is where freeze frame can help you too, because freeze frame tells you engine RPM, temperature, engine load, things like that, that the conditions that were occurring when the code was set. So you got your diagnostic trouble codes. They should point you in a general direction for what system we got here, right? You know, if the car's not running right, I said this before, it's not doing one of those things right. You know, it's not taking in an air-fuel mixture, or it's not, you know, it's not, hang on one second here. Okay, had just a little interruption there. There was a little noise. So what was I saying? I was saying that one of the systems, something's not happening right. You know, intake's not happening right, compression's not happening right. So what are the problems here, right? If I got a cylinder misfire, you know, what is it? Is it a compression problem? It could be. How can I tell the difference? If it only misfires on acceleration, for example, it's probably not a compression problem. Compression tends to be either good or bad. Doesn't really change with engine operating conditions, right? If a problem only happens cold or only happens hot, probably not something like a bent valve, right? That's going to be pretty consistent all the time. But if it's an ignition misfire, bad coil, weak coil, that might happen under load, right? And not happen at idle, decel, cruise. Fuel problem, you know, what's your concern? If you have a lack of power, maybe your fuel pressure is low. If you have a misfire, maybe you got a bad injector. You know? Air induction, we could have vacuum leaks. We could have, leaks in the air inlet tube between the mass airflow sensor and the throttle body. So, yeah, these are all the different systems, the different sorts of things that they can cause. EGR, it can cause stalling, things like that. Transmission, I told you about the Renault Alliances, right? They can mimic engine performance problems. You got a bad torque converter, that can be a lack of power concern. If you have an electronically shifted transmission that's not downshifting into first when you come to a stop, or even a manual, old-fashioned transmission, they'd have sticky governors, and sometimes you'd come down to a stop sign and it would downshift into second, but it would never downshift into first. When you want to take off, you're taking off in second gear. So you have this lack of power concern. So you may not be able to actually identify the system by just by the symptom, right? And by the trouble code, but you may. What you're trying to do is you're trying to narrow things down. You're starting with the entire vehicle. Between your, figuring out when the symptom occurs, are there codes, things like that. You're trying to narrow it down. You're trying to eliminate things that wouldn't be the problem, right? Here's one that only takes a minute, but can save you a whole lot of time. Every once in a while, the visual inspection finds the problem instantaneously. So Check for loose, disconnected wiring connectors. Literally tug on them, make sure they're snapped in place. Loose, disconnected, or cracked vacuum hoses, other physical signs of damage. We're talking a quick check here. We're not saying that you spend a half an hour on this. You're spending, a minute, 2 minutes, and you might save an hour because you see something before any kind of pinpoint testing brings you to that. So it's always worth a quick look. You got an oxygen sensor code, you look and the wires are falling off of it. Case closed, right? You don't really need much more diagnosis. Okay, and then diagnostic tests, or another term might be pinpoint tests, right? Sometimes, or I would say usually, the way this goes, right, is you have a customer concern, and maybe you have a check engine light. You check for a code, and that code tells you, right, when you look up that code, there's a diagnostic routine associated with that diagnostic trouble code. So you just follow that like a flow chart, right? So, check this, check that, and it'll just tell you what to do. The real challenge, I guess, is when you don't have a code, what do you do? What tests are available to you? And so that's what we're going to go through, in next week and things like that. Other tests that are available. We can use a scan tool and do fuel trim, right? So this is using a scan tool, but we're not using the onboard diagnostics of the car. We're using our own observations. The scan tool is just to read data. We can do fuel pressure testing, vacuum test, and some of these things we've demoed or done in the lab, right? Compression test. I know everybody got to do a compression test. Cylinder leakage test. Maybe a timing advance test. I have a little video that I did in the shop on that Subaru engine that's on a stand. I'll stick that in at the appropriate time, where you can see we tested the NOx sensor to make sure the NOx sensor is working. Cylinder balance, that can be done on some cars right in the scan tool. Ford has it built right in. Injector balance, again, some vehicles that's built right into the diagnostic software in the PCM, so you can just access it with a scan tool. Others, you have to do it manually. So we're going to talk about all of these sorts of testing, and unfortunately, with the shop kind of shut down, some of these we may never get to actually demoing. We've done a lot of them. I know we've looked at a lot of them, but some of them we may not. One that's not on here is relative compression. And we'll talk about that, I guess, with the compression test. But it's a very quick way of looking for one bad cylinder. One burnt valve, one cracked piston, or something like that. So hopefully this is giving you sort of an overview, and what we'll spend the next few weeks is just getting into all of these individual tests. We were talking about verifying the condition, retrieving trouble codes, diagnostic tests, et cetera, and so we were here, this list of tests that we can do, and we were about to starting with talking about fuel trim. But something else I wanted to show you, here I brought up a 2018 Ford Explorer, because in the lab video you'll see this is one of the vehicles I use for the lab. And under engine, if I go down here to initial inspection and diagnostic overview, diagnosis and testing, it says refer to engine for basic mechanical concerns, right? 303-000. So I'm going to click on that. And it kind of runs us through the same sort of thing that I talked about as far as verifying the concern, doing a visual inspection, and on, using a scan tool, making sure that the scan tool can talk to the vehicle, retrieving diagnostic trouble codes, etc. So some of the things that I just thought were kind of humorous is when we talk about engine noises. So when we get down to that, I just want to show you some of those. It's actually kind of funny. But here's a list of different symptoms, right? Difficulty starting, some of the possible sources and what to do about it, right? And we get down to poor idling. We have engine runs rough, excessive oil consumption, oil in the coolant, coolant in the oil, insufficient power, and all the different things that could cause that, right? Black smoke, blue smoke, white smoke. This is really kind of just kind of funny. Some of the different noises. This is noise, vibration, and harshness concerns, right? NVH. And so we have rattle, right? Whine / moan, clunk, drone, drumming, rattle, moaning, whine, clunk. But then it starts to get kind of funny. And I don't know how to describe every one of these sounds, So we have hooting. We have humming. We have whining, whistling, right? Hissing, grinding, tapping. Still pretty normal, right? Upper end ticking, and under different conditions, right? So worse when the engine's cold, stuff like that. We get into some of these crazier ones that I'm not sure I can really explain to you. We have slapping, knocking, and then some of my favorites here, vibration, shudder, bongo. I'm not sure exactly how to describe bongo. Chatter, chirping, clicking, clatter, crickets, quacking might be my favorite right there, quacking. So if a customer comes in and says their vehicle is quacking, if it looks like a duck and sounds like a duck, I guess, scratching, squeaking, squealing, thumping, tin-like. So my point here is the list of possible symptoms and noise and vibration symptoms and all that is pretty huge. So this is going to be one of your biggest challenges, is to figure out, what exactly is it I'm trying to fix. But these are handy little charts, that can give you, if I get back up near the top, when we get not so much the noise diagnosis, but performance diagnosis. For every symptom, it can give you a list of possible sources, things that you might think could cause that. And then, of course, if you determine that that is the problem, then, they give you the action to take for that. So, for example, if we have a burnt valve, install a new cylinder head. If we have a worn piston, install a new piston. Worn piston rings, new piston rings, pretty obvious, right? Poor idling, what could cause poor idling? Well, we could have vacuum leaks, we could have a bad EGR system, not closing off, right? So you're leaking some exhaust gas in at idle, which is bad. Ignition, cooling system, fuel system, incorrect valve clearance. So these are different things that could cause the symptom of poor idling. When we get down to insufficient power, ignition, blockage in the intake, blockage in the lubrication system. Wow, so I guess we're fighting the oil pump. Fuel system, turbo problems, exhaust problems, too much oil, excessive load from accessories, we're overheating, we might have a plugged exhaust system, maybe the tires are the wrong size, or the brakes are dragging, or the transmission is slipping. Just instead of you having to memorize every possible thing that could cause that symptom, here's a pretty exhaustive list for you. And so, you're going to be able to take some of these and throw them out immediately based on your observations, your visual inspection, what it sounds like, what it feels like. But at least it gives you somewhere to go when the problem is non-obvious. Right? If I go up and kind of pick the same sort of thing, change vehicle, let's see if it's in here still. A lot of people have been in here. 2015 GMC, I use this in the lab video as well. And if we pick engine and, symptom-related diagnostic procedures, right? So we have another here, list of symptoms. Base engine misfire, engine noise on startup, engine noise under load, engine misfire with excessive oil consumption. Here's possible causes, here's the correction, right? So they do it a little bit different. We do component tests and general diagnostics here, right? Here's something we'll actually do in the lab, cylinder deactivation system test. We'll talk about this though when I do the lab video for it. It's something I can do with a scan tool without taking the vehicle apart. But again, when you look at testing and inspection, we can have a list of symptoms or specific tests that we can do. Or of course, if we have a diagnostic trouble code, then we're just take a P code and obviously whatever that code is, and let's go down to a misfire of some sort. It's going to give us a description of the system, conditions for when the diagnostic trouble code runs, what it takes to set the code, what happens when the code is set, how we clear it, and some extra information, right? And then it goes into step by step. Do this, check that, step by step, just following us through. So sometimes we're just following a code, but other times, like I say, we are following a symptom, right? So we, symptom-related diagnostic procedures. We have a base engine misfire. Now, what does base engine mean? We talked about this before. This means it's not the fuel system or the ignition system or anything like that. It's, the base engine is what's been around since, for 100 years, right? Crankshafts and connecting rods and pistons and valves and push rods and cam lobes and rocker arms, and that's base engine. The ability of the engine to draw in air, compress it, and then get rid of it. Okay, so I'll close down all data here, and let's go back to our slides. So the tests we want to go through, and this is not an exhaustive list, right? We may think of other things as we go. Fuel trim, so that's strictly a scan tool thing. That's something I can demo for you in the lab videos, right? Fuel pressure, unfortunately, I do not have the equipment at home to demo this test, so hopefully we get back into the shop before the semester ends, or maybe you get it in the fuel and emissions class. Vacuum testing, I know we did a worksheet on this already, so I'll just talk about that. I know we did compression and cylinder leakage. We haven't really done timing advanced cylinder balance or injector balance. So I have, as part of my lab video, the cylinder balance, that which you can do with a scan tool. Did that on the Ford, so you'll get to look at that. But we'll talk about it in the lecture as well. So let's start. Let's start with fuel trim, all right? We can't really talk about fuel trim diagnosis until we talk about what fuel trim is. So let let me go back to just talking to you for a minute. So what is fuel trim? What are we talking about? And fuel trim essentially is a correction that the computer does for a miscalculation that's made in the fuel delivery or the fuel quantity calculations, I guess. You know, how much. So let's start from the start, right? How are the fuel injectors controlled by the PCM? How does the PCM decide how much fuel to inject each time the injectors operate? So you have a bunch of sensors out on the car. You have, depending on the system, right, you've got engine RPM, right? It's getting that off the crankshaft position sensor, probably. You have things like engine temperature, intake air temperature. You may have manifold vacuum or what they call manifold absolute pressure, you know, MAP. You may have mass airflow, MAF sensor. Typically, mass airflow cars and MAP sensor cars operate a little differently. You'll have accelerator pedal position, throttle position. So all these sensors out on the engine or on the accelerator pedal too, on the transmission, you know, vehicle speed, all of these things feeding information into the computer. And it's the computer's job to take that information and it's really kind of a measurement of a couple things. How much air is coming into the engine and how much load is the engine under. And then to add in the correct amount of fuel so that we get the correct air-fuel ratio. So the really simple explanation, if the computer just looked at the mass airflow sensor, so this is an airflow meter, it's measuring the air coming into the engine by mass, so not by volume, but by mass. And then putting the correct ratio of fuel in. Pretty simple, except there are things that have to be compensated for, right? We don't run the same air-fuel ratio at idle or at cruise that we do under heavy acceleration, right? If you stomp on that loud pedal, the computer needs to add additional fuel, not just your basic stoichiometric air-fuel ratio. If the engine's cold or the intake air is cold for that matter, that's going to affect how much fuel is injected. Yeah, engine load, engine RPM, what gear we're in, whether the air conditioning compressor is engaged or not, whether the fan's running or not. You know, these all go into the whole load characteristics of the engine at the time and into, you know, just what kind of air-fuel ratio is required for those particular operating conditions. So if the computer just did that, right, just measured engine RPM, airflow, load, things like that, temperature, made a calculation, and delivered the calculated amount of fuel through the fuel injectors, what are the odds that it would get it exactly right? You know, that every single possible variable was accounted for. Probably not really too good. So what's required then is after the computer goes through this process, and it does it over and over again, so it goes through this process of determining how much fuel is required, and then it delivers that amount of fuel. The next step, it has to look and see how it did. It has to look at the results and determine, was that enough fuel? Was that too much fuel? Am I too rich? Am I too lean? And this is where the oxygen sensors come in, or the air-fuel ratio sensors, depending on what kind of car you're working on. And we're talking about the pre-catalyst sensors, the upstream oxygen sensors. Those are the ones that are seeing what's coming out of the cylinders, coming out through the exhaust and seeing if we're too rich or too lean. The post-cat ones, that's affected by the catalytic converter, so that's not going to be an accurate representation of whether we're too rich or too lean. So, computer takes in information, uses that information to determine how much fuel to deliver, delivers the fuel, and then looks to see how it did. If we're too lean, then we have to add a little additional fuel. And if we're too rich, we have to add a little bit less fuel. So there's a concept called open loop fuel control and a concept called closed loop fuel control. Open loop fuel control is when there's no feedback. In other words, the computer delivers the fuel and just hopes it's right. That's what happens when the oxygen sensors are not operational. So when are the oxygen sensors not operational? Well, if they're broken, obviously, or worn out. But even on a perfectly functional car, when you first start an engine up from cold, the oxygen sensors aren't working yet. So we are in open loop fuel control. And years ago, we were in open loop fuel control for a long time until the hot exhaust gases heated up the oxygen sensors. Now, for the last probably 20 years, we have heated oxygen sensors. So what happens is as soon as the vehicle starts running, within a very short period of time, less than half a minute probably nowadays, those electric heaters have gotten the oxygen sensors hot enough that they're functioning. And once they're functioning, then they can start providing feedback to the computer. So let me use an analogy here. Let's say that open loop fuel control would be like this. An open loop system, let me use the heating of this room that I'm in, all right? We can know the cubic footage, how many cubic feet of air are in this room. We can know what the insulation value of the walls and ceilings, there's a window over here on the other side of this bookcase. We can know the R value of that, the carpeting, and the size of the heating ducts coming in here. We can calculate all that. And theoretically, knowing the outside temperature, knowing the temperature we want inside the room, and knowing what the level of heat loss will be through the walls and ceiling, we could decide how many BTUs of heat need to come into this room every hour. And so if we're going to lose, 10,000 BTUs, then we need to add 10,000 BTUs in order to keep the room temperature the same. And if our calculation is absolutely perfect, this room temperature will stay the same. Now, what happens if this light bulb burns out? There's a heat source gone, right? Or somebody cracks a window, or another person's in the room, their body heat. All of a sudden, that's going to throw our calculation off, and the room is either going to gain temperature or lose temperature. So open loop control of something doesn't really work, right? Nobody heats their house that way. Nobody has a furnace that's set to deliver a certain amount of heat per hour and just hope it's right? What do you have in your house? You have a thermostat. So if you want your room to be 72 degrees, you set the thermostat for 72 degrees. If it gets colder than 72 degrees, the heat comes on. If it gets warmer than 72 degrees, the heat goes off. So your average temperature in the room is 72 degrees. That is a feedback loop, right? So the thermostat controls the furnace, which then affects what the thermostat reads, which then controls the furnace. And, we're going around and around in a loop, feedback loop. So our fuel control systems, when we're in closed loop, they are a feedback loop. So the computer injects fuel, causes fuel to be injected through the fuel injectors, and then the results of that fuel calculation show up on the oxygen sensors or the air-fuel ratio sensors, letting the computer know whether it was didn't calculate enough fuel or calculated too much fuel. So fuel trim is the process of then making that adjustment to the amount of fuel delivered and getting it right. So we'll take an example. Engine's running. The computer looks at mass airflow. It looks at engine RPM. It looks at throttle position, accelerator pedal position, engine coolant temperature, calculates how much fuel to inject for the particular RPM and load scenario that we're in. Injects that fuel and then looks at the oxygen sensor or air-fuel ratio sensor. If the amount of fuel injected is too much, right, then we're going to be too rich. What will the computer's response be? Well, the computer then will apply a negative fuel trim number to the calculation. So the next time the computer figures out how much fuel to inject, which is only milliseconds later, right? It takes that calculation and then it applies that negative percentage to it, and so injects a little bit less. So if our fuel trim number is negative 5%, what that means is the computer calculated a certain amount of fuel, and now it's subtracting 5% to try to get it right. So normally, most vehicles do not have a 0% fuel trim number. If you look at the scan tool, none of them get it 100% right all the time. So the fuel trim number is always at least a few degrees. Rule of thumb for me is if we have single digits fuel trim numbers, preferably low single digits, under 5, but single digits, then there's probably nothing really wrong with the way the fuel control process is happening, right? If the numbers begin to get into double digits, then that's an indication to me that we are compensating for some underlying problem. Let me give you an example. If for some reason the fuel pressure was low, whether that be a leak in the line or a bad fuel pressure regulator, whatever reason, the fuel pressure is low, then when the computer delivers fuel to the engine, it's not going to be enough. It's going to be less than expected. What will happen? The oxygen sensor will report that we are too lean, and so the fuel trim number will go positive. We are adding some fuel to the calculation. So let's say that the fuel pressure is just a little bit low, just a tiny little bit, 1 psi, right? Our fuel trim number is going to be a small positive number. But let's assume that the fuel pressure is significantly low, right? And so our computer has to keep those injectors open longer in order to deliver enough fuel. Our fuel trim numbers are going to be a high positive number, 12, 15, 18, who knows? It's hard to generalize. That's going to tell me that there's some sort of an issue. So let's break this down into two categories. We have a category where we have fuel trim numbers that are low, which means there's some slight inaccuracy, but it's compensated for. The computer is able to compensate, and no action is necessary. In other words, there's nothing wrong. If it ain't broke, don't fix it, right? the vehicle is running at the correct air-fuel ratio. It's being corrected by the fuel trim, and it's running at the correct air-fuel ratio. Now let's take situation B, where the problem is so severe that the computer keeps adding fuel, trying to get our oxygen sensors to read correctly, and regardless of how much it adds, we're still lean. So it's unable to compensate for the problem just by simply increasing fuel delivery. At some point, it'll give up, and it'll set a code saying that, either that the fuel trim or the adaptation or adapt, has reached its maximum, or it'll give us a P0171, lean code or something like that. What that tells you, if you see that code, is, hey, there's something enough wrong, right? Significant enough that the computer gave up trying to compensate for it and just flagged it as a serious problem. So we have basically compensated and uncompensated. Take this into like the first aid world, right? Talk about maybe being cold, right? So you get a little bit cold, you're outside, you didn't wear enough, maybe you shiver a little bit, right? And that shivering generates enough heat that keeps you from freezing to death. So everything's good, right? If the shivering doesn't work, then it stops, and you're in this uncompensated hypothermia sort of situation where if something's not done about it, you're going to die. Not good, right? So the uncompensated, fuel delivery problem, eventually the engine's going to give up, or the computer's going to give up and say, look, I tried adding a little more fuel, and I tried adding a little more than that, and a little more than that, and we're still too lean. So we're just gonna put the check engine light on and get this vehicle looked at. Let's go back to the slides again for a minute, and we'll talk about this. Get rid of my video. Okay. So how do we look at fuel trim, and how do we use the fuel trim numbers to help us diagnose some sort of a concern? So, and then what's going to bring me to looking at fuel trim in the first place, right? Usually, it's going to be a lean or a rich code that's going to bring me here. So we need to connect an OBD2 scan tool, access the data stream, and look at fuel trim. And you're going to see two numbers for that. Well, you may see four numbers, all right? You're going to see short-term fuel trim, and you're going to see long-term fuel trim. Ooh, that's a nasty number, or let's see here. So we're going to have what you might possibly see as short-term fuel trim, long-term fuel trim. And they will be in a percentage. That's how they'll be listed. So if you see single digits, it's 5, it's 4, it's 3, you don't have a problem, right? But the thing that you should understand is that these fuel trim numbers are calculated not just for idle. So you might have a one fuel trim number at idle and a completely different one driving down the road. The computer uses a different table for idle than it does for driving down under load. It uses a different table for idling in park than it does maybe for idling in drive. it may use a different table idling in park for revving it up in park. So you could find that fuel trim numbers are different at idle than they are driving down the road. So what you want to know is, what are they under these different conditions? If the fuel trim numbers are only out of whack at idle, then you're probably looking at a vacuum leak, a cracked vacuum hose, a bad intake gasket, maybe a little bit of a crack. In other words, it's going to be a small leak. And so what does a vacuum leak do for you? What a vacuum leak does is it allows unmetered or unmeasured, or what some people call false air, into the engine. So this is air that's in the engine, but the computer doesn't know about it. If it doesn't know about it, it's not adding fuel, and so we're going to wind up too lean. So if you have a small vacuum leak, it accounts for a very small percentage of the air flowing into the engine. Think about that. If I have, I'm just going to throw numbers out here, right? If I had, let's see, 50 cubic feet per minute, right? I'm just going to throw that number out there, right? So let me write that down. So 50 cubic feet per minute, right? Now let's go with 650 cubic feet per minute, something more realistic, right? And I had a vacuum leak that was allowing 4 cubic feet per minute to get into the engine without going through the mass airflow sensor. You know, what kind of number is that, right? So if I pull out my calculator here, right, and I do 4 out of 650, it is 0.006%. That's not exactly earth-shattering amount of excess air, right? Let's say that we have, let's say we're at idle, right? And we have only 50 cubic feet per minute. And let's do that same 4 CFM vacuum leak, right? What does that give us? Well, 4 out of 50. Almost 1%, or yeah, 0.08, 8%. All right, so that's starting to get more significant, right? Let's say we have a 10 cubic foot per minute vacuum leak at idle, where the entire airflow coming through is 50. That means 20%, 1/5, right, of our air is unmeasured. That's huge. That's going to cause a really serious problem, right? We have 50 cubic feet per minute coming into the engine, and the computer doesn't know about 10 of them. It's going to be very far off on its fuel calculation at idle. Now we start driving down the road. We have the same vacuum leak, right? The same, right here, 10 cubic feet per minute. Where are we? Right here. That hasn't changed at all. Okay. That's not what I wanted to do. I wanted to get rid of this. No. Okay. Let me go back. We got a 10 cubic foot per minute vacuum leak, and our total airflow is 50. That's 10 out of 50. That's 1/5, 20% of our air is unaccounted for. Computer doesn't know about it. We're going to be way off on our fuel calculations. Now we take that same vehicle and drive it, and now there's 500 cubic feet per minute, right? You can see that the effect of the air leak now is, 2%. instead of, and that's not even right, 10 out of 500 unaccounted for cubic feet per minute. Very, very small effect on the engine operation. So if I have this small vacuum leak, 10 cubic feet per minute here, it will be significant at idle, right? But when we start accelerating and we start getting more air into the engine, it will become less significant. So what I'm trying to tell you is, if your fuel trim numbers are way off at idle, but are not off when the engine is going faster, your most likely problem is a vacuum leak of some sort. On the other hand, if our fuel trim numbers are off across the board, now it's more likely you got a bad mass airflow sensor. Or, your fuel pressure is really low or something like that. I would say mass airflow sensor is probably the most likely if your fuel pressure or if your fuel trim is off across the board. So if you're only off a little bit and the PCM is able to compensate, so, if we have a small, tiny leak, our fuel trim numbers might be 8, 9, 10%, whatever. There will be no symptom, there will be no code. It's when that leak starts getting up into the, double digits. And I've seen vehicles allow it to get as high as 25% before flagging a code. I've seen others that at 15% it flags a code. All right, let's get to the question here, right? So question 1, vehicle comes in with no check engine light. The complaint is for poor fuel economy. So you decide you want to check the fuel trim. You see that the long-term fuel trim is +6 and the short-term fuel trim is -3. What is the combined fuel trim? So if you want to know what the total fuel trim is, you just add the two together. If you take +6 and -3, the result is +3. So the combined fuel trim is +3. What does this indicate? It indicates that you don't have a fuel trim problem. Now, that's not to say you don't have a fuel economy problem, but it is not a fuel control, fuel delivery, fuel trim issue. Next question, vehicle comes in with a code for a lean air fuel mixture. You check the vehicle's data parameters and find the long fuel trim parameter reads greater than 15% at idle, but when driving at higher RPMs, it is reading single digits. This most likely indicates, now this is exactly what we talked about, most likely indicates a small vacuum leak. And then when we increase the overall airflow, that small vacuum leak becomes much less significant than it would be at idle. So that's the key. It's a percentage thing, right? If we have a small percentage of unmetered air, it's going to have a very small effect on our fuel trim. If we have a large percentage of unmetered air, it's going to affect our fuel trim drastically and across the board. Okay, stop sharing this a minute. And we'll turn me back on here, right? So I know, fuel trim is, for some reason, it's an issue that confuses people a lot. But the thing is, it's one data point, one thing that we can use to see, is the computer able to accurately control the air-fuel mixture? Or are things too far out of whack that the computer has to give up and get you to look at it, right? So if you don't have a code, you probably don't have a fuel trim problem, but that doesn't mean, you could have a small vacuum leak, so there is something wrong with the car, right? Technically, there's something wrong with it. But if it's small enough that the computer is able to compensate with fuel trim, it will have no effect on the engine's operation. It won't have any drivability symptoms, and it won't cause a code. So that's important to realize. Okay, to wrap things up, let me share with you, let's see, an all data screen. And let me turn my video off. Okay, so I've brought up that 2015 Sierra, and I'm going to go to all diagnostic trouble codes, P code charts, and I'm going to pick a P0171. So you'll see that P0171 is fuel trim system lean bank 1, and then rich is 172, bank 2 lean is 174, bank 2 rich is 175. So I've picked P0171 fuel trim system lean bank 1, and we can, if you want, you can go to all data and bring this up, but because I don't want to read the entire thing to you, but there are conditions that need to be met in order to even run this diagnostic, right? So there's a whole list of diagnostic trouble codes that it says can't be set. And if you look, essentially, any of these would eliminate the closed loop fuel control system probably from even working, right? And can't be in the middle of an evap leak test or catalyst monitor test, or so these are things that would throw off fuel trim numbers, right? We got to have certain intake and engine coolant temperatures and map and speed and mass airflow readings and how much fuel there is. So it runs continuously as long as all those conditions have been met. Now that seems like a lot of conditions, but when you think about it, most of the time when you're driving your vehicle, you don't have any of these codes, right? Most of the time, all of these conditions have been met, unless we have just started the vehicle or if it's in the middle of a catalyst monitor test or an evap test, right? But most of the time, this diagnostic is just going to run continuously. So what are the conditions for actually setting the code? If the average long-term fuel trim weighted average value is greater or less than a calibrated value. If it's present for approximately 3 minutes. So you're not going to get a code as soon as the fuel trim goes above or below a certain value, right? This test is going to be running all the time. And if it sees the fuel trim out of whack for 3 minutes, then it knows there's a real problem. There's all kinds of things that could temporarily throw the fuel trim off. So what happens when the DTC sets? It says they're type B diagnostic trouble codes. We'll talk about that at another time. But that determines, whether the light comes on, whether a pending code is set or whether an actual code is set. Things we really talk about more next semester, right? Gives you some diagnostic aids, and it tells us that, we want to watch the oxygen sensor parameter. It should vary from 40 to 900 millivolts. All right, so the oxygen sensor is working, responding. Here's the key. The normal short-term fuel trim and long-term fuel trim parameters should be between +10 and -10, with 0 being the optimum with the engine at operating temperature. So if the computer's air fuel calculations were perfect, fuel trim numbers would be at 0. That's rarely the case. There's usually some adjustment required, right? But they would like 0. But as long as it's single digits, like I said before, we're good, right? Any unmetered air into the engine causes this DTC to set. Thoroughly inspect all areas of the engine for vacuum leaks. I'm going to tell you the single most likely cause of a lean code is some sort of vacuum leak, whether it be a vacuum hose, a bad intake manifold gasket, or say somebody has not properly installed and tighten the hose between the mass airflow sensor and the throttle body. Or sometimes they crack because they do flex. Frequently, the mass airflow sensor is mounted near the air cleaner, which is attached to the car body, and the engine moves under acceleration and deceleration. It moves a little on the mount, so that hose that connects the mass airflow sensor to the engine is constantly flexing. And over time, they do have a tendency to develop cracks. All right. So it says a mass airflow sensor condition can cause this DTC without setting a MAF DTC. If there is a MAF sensor condition, the MAF sensor parameters will appear to be within range. So I don't know if you've ever heard the expression, you know, that we talk about dumb people don't know they're dumb, right? Or stupid people don't know they're stupid. Well, mass airflow sensor that's reading incorrectly doesn't necessarily know it's reading incorrectly. What can go wrong with a mass airflow sensor without it completely failing? They rely on air coming in contact with wires on the sensor. If those wires should become coated with dirt or become corroded, and the air is not making good contact with those wires, they're going to do a poor job of measuring the amount of air flowing into the engine. They will underreport how much air is flowing in, right? But, you know, the numbers that come out of them will be reasonable. They won't be completely whacked, right? It's just, you know, reporting less air than is actually flowing in. Enough that the engine's not delivering enough fuel, or the computer's not delivering enough fuel, right? So definitely air leaks and mass airflow sensor problems can cause these lean codes, right? It says verify the air filter is the correct one. Certain aftermarket air filters may cause a code to set. A lot of people like to, you know, replace their factory air filters with those K&Ns. Certain aftermarket air induction systems or modifications to the air induction system may cause a DTC to set. Certain aftermarket exhaust system components may cause a DTC to set. Well, that one I haven't heard before, so I got to think about that a little bit, right? So, you know, they're going to run you through step by step here. But I just wanted to point out, you know, they're telling you that the numbers that I wanted to see in here is this plus or minus 10%, right? Hoping for zero. And that vacuum leaks are a huge cause. And mass airflow sensor is probably like the second leading cause. Right? So let me stop sharing that and just kind of wrap this up a little bit. So next week we'll talk a little bit about fuel pressure. I'm trying to figure out how to get some video of this kind of stuff to demo for you for the lab portion, the lab videos. I'm still working on that. You know, so don't panic just because we're not in lab. I'm still working on ways to demo things for you and to get you to write up some reports so I can give you a grade for the weeks we're missing. I'll keep you posted. Just keep an eye on your email. And until next week then, as far as the lecture portion of it, that should do it.